Integer factorization is the process of breaking a composite number down into its prime building blocks. Historically, this has been a computationally expensive task, which is exactly why it forms the bedrock of modern cryptography. The most basic approach is trial division, which involves testing every potential prime factor one by one. This method scales poorly, creating immense computational drag as target numbers grow exponentially larger. But by expressing integers in a specific algebraic format, we can bypass trial division entirely. This framework shifts the problem from guessing random prime factors to finding a single integer parameter that solves a quadratic polynomial. Traditional arithmetic division reaches a hard limit with large integers. Solving this requires a different algebraic approach to primality testing and factorization. We begin with a parametrized quadratic equation that will serve as the engine for this algorithm. The equation structure is x squared minus the quantity 6r plus t times x plus k minus r equals 0. We extract its discriminant, delta r. The roots are whole integers only if this evaluates to a perfect square. The entire algorithmic goal is now an iterative search for the variable r that satisfies this perfect square condition. By shifting integer factorization into the domain of quadratic discriminant analysis, the problem is reduced to a bounded search for a perfect square. First, the target composite number, n, is mapped onto a standardized base 10 algebraic structure. We define this initialization format as n equals 10k plus s. This isolates k as the integer quotient and extracts s as the single-digit remainder between 0 and 9. The remainder s determines the factor carity, establishing strict even and odd mathematical constraints. This base 10 fragmentation ensures that any integer, regardless of size, provides standardized constant variables, k and s, to parameterize our sieve. Recall the variables needed for the quadratic equation, k, r, and t. We have k, but we need to derive t. The variable t is a constant derived directly from a mathematical combination of k and the parity constraints associated with s. That leaves r as the iteration target. It is the only unknown variable left in the algorithm. We establish the boundaries of the search space by starting the algorithm's iterative loop at r equals 0. The upper limit of the search space is also fixed. The variable r must be less than or equal to k. If the algorithm increments upward and reaches k without finding a perfect square discriminant, it hits a boundary known as the trivial solution. The algorithm bounds the search space completely. It is impossible for r to exist outside the established range of 0 to k. We can observe the first practical application from the source material, using a known composite number. F of n equals 143. This grid displays the mapping for 143. Using n equals 47, we extract constants k equals 4 and s equals 7. The derived constant t equals 0. Beginning the loop at r equals 0, the calculation outputs a parity-adjusted delta of 4. We evaluate the output. The discriminant delta equals 4. We verify the perfect square constraint. 4 is a perfect square, resolving to 2 squared. By finding a perfect square on the very first iteration, the algorithm proves 143 is a composite number almost instantaneously, without a single division operation. Finding r equals 0 is only step 1. We must now plug this non-trivial solution back into the primary quadratic equation. We substitute r equals 0, t equals 0, and k equals 4 into the base polynomial. We simplify the equation to solve for the roots, x. Next, we translate the mathematical roots x back into the physical prime factors p and q using the text's defined parity mapping. The final calculated prime factors are 11 and 13. This confirms the result. 11 multiplied by 13 equals 143. The abstract algebraic mapping successfully and deterministically resolves into the precise physical prime factors of the composite number. We can contrast this composite factorization with the algorithm's behavior when analyzing a true prime number, using the text's case study of 1013. This split screen compares our previous test with the parameters for 1013, specifically noting the upper iteration bound of k equals 33. The loop executes rapidly as it increments r upward from 0. Observing the delta r outputs, we see that none of the values generated are perfect squares. The algorithm hits r equals 32. The source text marks this outcome as pasta solution, no solution. At r equals 33, it reaches the trivial solution. Because no perfect square was found before reaching k, the search space is officially exhausted. The mathematical conclusion is strict. The total absence of a non-trivial perfect square discriminant is absolute proof of primality. The sieve proves primality not by attempting to divide by every possible number, but by fully exhausting a strictly bounded parameter space. There is a stark difference in efficiency between brute force division and finding polynomial roots. The method leverages the inherent mathematical parity of prime numbers to exactly map them to geometric, deterministic curves. Scaling this method to larger cryptographic numbers relies entirely on optimizing the search for perfect squares. While advanced sieves exist, this specific parameterization provides a unique algebraic lens on integer behavior. Prime numbers, often viewed as randomly distributed, are bound by strict polynomial rules when viewed through the right mathematical framework. By converting factorization into discriminant analysis, this algorithm reorganizes a chaotic arithmetic chore into an elegant, bounded algebraic proof.